Hello, my name's Simon McIntosh-Smith. I'm a professor of high performance computing at the University of Bristol, and I'm the lead investigator of the Isambard 2 ARM-based supercomputer. I'm going to tell you a little bit about that today. First, some motivation. Why is it that we're looking at doing this? Well, as you know, ARM's having a huge impact on the computing space. And in fact, by the end of last year, by the end of 2020, over 180 billion ARM-based chips had shipped in total, and nearly 7 billion of those had shipped just in the last quarter of 2020, which is a phenomenal growth. And it's this huge growth that really we're looking to see if we can exploit as a disruptive technology into high-performance computing. And we're seeing other sorts of impacts from this as well. This is a chart that AnandTech recently produced comparing the performance progress on Apple's ARM-based processors compared to desktop processors. And you can see there's a really classic Hayden Christensen disruptive trend going on here, where the performance starts off being a lot lower than the higher end desktop space. But over time, because it's being driven by a really large space with much larger funding, you can see how they're on crossing trends. And the proof point of that has really just arrived in the last few months with Apple's new M1 chip, the A14, with some phenomenal performance that's greater than almost all today's desktop and laptop processors, at least in single thread performance. It's really quite something. And in fact, I'm talking to you right now on an Apple M1 based laptop. So we're actually using this technology today. It's finally here, even though it's been predicted for quite some time. So the whole kind of ARM trend has been something very interesting that we wanted to explore in high performance computing. And through that, in the UK, we have a very broad ecosystem of high performance computing services that we deliberately try to explore the whole gamut of the solution space. So we have tier one services in the UK like Archer and the Met Office and Dirac services. And then we also have tier two regional centers where we like to try a very diverse set of different technologies. And I'm actually representing the GW4 service, which is the Great Western Four Alliance. That's 4 universities in the southwest of the UK, from Bristol, Cardiff, Exeter and Bath. And we've clubbed together to explore these ARM-based technologies. And we're doing that through this Isambard supercomputer, and now it's recently been upgraded to Isambard 2. Isambard 2, we've had £4.1 million of funding from our research council, which is the Engineering and Physical Sciences Research Council. We've teamed up with the Met Office and also with HP, Cray, Fujitsu and ARM, and we're running a production ARM-based service. And we actually started doing this with Isambard 1 way back in, our first funding was in 2016, and the first service went live in 2018. The first service was £3 million. And that was the first production ARM-based supercomputer in the world. People were coming to use Isambard to try ARM, and then they just stayed to use it like any other supercomputer, which was a real success for us, that you could just use this. Even though it was a totally different architecture, you could just compile and run your code like you could on any other system, and it just worked for the most part, which is really good. The Isambard 2 production system, the main system today, is about 21,500 cores of Marvell ThunderX 2. That's our big workhorse. It's running flat out all the time. It's really stable. We've had pretty much no unscheduled downtime for the whole time it's existed. Has a really nice Cray software stack on it with all of the Cray tools and libraries and compilers and so on, as well as all of the open source tools, so GNU and Clang and all of those things. We've also got something called a multi-architecture comparison system, which we use for having a little bit of everything else. So all of the other different kinds of CPUs from Intel and AMD and IBM and GPUs as well, so that we can do nice benchmarking across different technologies. And the system's actually hosted for us by the Met Office down in Exeter. The exciting recent thing we've had with a recent upgrade is we now have some of the Fujitsu A64FX processors as well from Fujitsu. This is the same processor that's in the Fugaku #1 supercomputer in the world that's at Riken in Japan. We have 72 nodes of this A64FX in an HP Apollo 80 system, 3,456 cores in these 72 nodes. But each one of those has really high floating point performance. And again, because it's coming from HPE now, we have the Cray software stack. So we have a Cray compiler again, as well as GNU ARM. And this is one of the few systems in the world where we've also got the Fujitsu compiler. So we have both the Cray compiler and the Fujitsu compiler, as well as the more open source ones, all on the one system. The Fujitsu A64FX is really quite an exciting processor. It's 48 cores, and they're at 1.8 gigahertz in the Isambard system, 4 NUMA regions within that one processor, about 2.7 teraflops of double precisions. That's very high for a single processor, and that comes from 2 512-bit wide vector units using ARM's scalable vector extension SVE. Has lots of memory bandwidth as well, because it uses the same kind of memory technology as a GPU. It has a terabyte a second to HBM2 memory technology, and the whole processor, including that HBM, is only about 170 watts running flat out. So the energy efficiency of this approach is really very high, similar in general to what GPUs have been achieving, but in a CPU style form factor, which is really impressive. What we've been doing recently is to evaluate the performance of the A64FX. We've been comparing it against some of the other ARM-based platforms which have been emerging. So some of these are in the cloud, some of these are available in Isambard. So for example, we've recently been comparing against Amazon Web Services Graviton 2. So this is Amazon's own ARM-based solution they've designed in-house. It's got 64 ARM sort of off-the-shelf cores. Also, something very new that's only just started to come out in the last few weeks is the Ampere Ultra ARM-based solution. Those are available through various cloud providers. We've had some early access through Oracle Cloud, where they have a dual socket 80-core system. So that's 160 cores running at 3 gigahertz. And these are fast, heavyweight cores. So that's 3.8 teraflops peak of double precision from these Ampere Ultra devices, and lots of memory bandwidth as well. And then we've also got, of course, our Marvell ThunderX2 processors, which are in the original Isambard production system. And those are 32 core parts, dual socket, so 64 cores. They're running at 2.5 gigahertz. Now, the nice thing is, on all of these different platforms, both the 2 that we have in Isambard and then the 2 on the cloud, we didn't have to do anything special configuring them. The ARM and GNU compilers ran across all of those, which was really nice. Cray tools were running on both the A64FX and the ThunderX2 platforms as well. And then additionally, we had the Fujitsu compiler on the A64FX platform. So that was really nice to try that. And we've got some, I'm going to show you some benchmark results from across all of those different ARM platforms. There's very few results you find today that compare all of the different ARM options, given that some of these are actually quite new. I think this is one of the very first performance comparisons of its kind that we'll share with you today. We'll start off with a really simple benchmark, which is called BabelStream. It's a memory bandwidth benchmark. It's based on Stream, but it's ported to many different parallel programming languages, and it runs on almost any hardware. So it'll run on all the different GPUs as well as CPUs. So here we're measuring memory bandwidth, and so higher is better. And we've got the A64FX, and then the Ampere Ultra, and the Amazon Graviton 2, and then finally Marvell ThunderX 2. And you can see the HBM2 memory on A64FX is really paying dividends here. 3 of the compilers were getting about 600 gigabytes a second. The Fujitsu compiler getting over 800 gigabytes a second. Remember, that's from one socket, right? That's from just one A64FX CPU. Whereas the Ultra and the ThunderX 2, those are dual socket platforms. Graviton 2 is one socket as well. So this is a very, very impressive result for A64FX. The Fujitsu compiler had a couple of extra tricks up its sleeve to do with streaming stores and invalidating cache lines that were about to be written to and overwritten, which the other compilers didn't know. So that's why it gets such a big has such a big advantage over the other compilers. But they're all impressive. To have 600 or 800 gigabyte a second of memory bandwidth achievable on one socket is the first that's ever been done on a single CPU. That's very impressive. That's BabelStream. Moving on to Cloverleaf. This is a hydrodynamics code. It's a very commonly used mini app or proxy app. Has lots and lots of different kernels. It's on a structured grid. It's generally classed as being memory bandwidth bound, but it does have some divisions and trigonometry, which actually those are very expensive on the A64FX. That's been designed to have relatively lightweight cores so that you can have lots of them in a small amount of silicon. So those are relatively expensive. And here we're showing runtime, and therefore lower is better, shorter runtime is better. Again, on A64FX, you can see the Fujitsu compiler was making a big difference. The GNU compiler wasn't doing very well here. Even the Cray compiler wasn't anything, and ARM compilers weren't anything close to the Fujitsu compiler for this particular case. So a good example of why you really want all of the different compilers to try where you can have them. You can see the Ampere Ultra CPUs did really well. They were the fastest ones we had in this test. That is 160 cores at 3 gigahertz. So that's a lot of performance. And in fact, these were performing very similar to top-end 64-core AMD Rome parts too. So this is about as fast as we've seen any CPU. So you can see that A64FX is actually doing really well to be beating those. Graviton 2 pretty good, and ThunderX 2 you can see the sort of previous generation starting to fall a bit behind on performance now. But A64FX is doing really well on that. Cloverleaf's also a hybrid code, so it runs using MPI and OpenMP. Typically, when MPI rank per NUMA region and then OpenMP within the NUMA region was often the best performance on Cloverleaf. So A64FX also doing very well for that kind of code. Then miniBUDE is a molecular docking benchmark, and it's a compute-bound code. So compared to the previous two that were about memory bandwidth, this is a compute-bound application. And on many platforms, many hardware platforms, we can get miniBUDE to achieving over 50% of the peak flops of the hardware. And that includes vectors, includes running on GPUs. So it's a really good one for seeing how you can do in terms of the peak flops of your hardware. Again, this is runtime, so lower being better. And interesting, this is one where we'd expect A64FX to do better than we've managed to achieve so far. Fastest platform we've had so far has been the Ampere Ultra, we're running on Oracle Cloud. That was doing very well. Again, that was similar performance to dual socket AMD Rome, so similar to 128 cores of AMD Rome. And really, A64FX should be doing about as well as that in that sort of ballpark. And it's a little bit behind, even with the Fujitsu compiler, which was the fastest of all of them, Cray being the next fastest. Single socket of Graviton 2 not doing too badly, ThunderX 2 a little bit further behind. But really, we would have hoped A64FX to be a bit closer to the Ultra performance. It's got about 74% of the peak flops of a dual socket 160 core Ultra system in the 48 cores of one socket of A64FX. So really, it should have been a bit closer to about 200 milliseconds instead of 400. So there's a bit more work to come there, and some of that's going to be in the compilers, and they're still a little bit immature. So that was a performance on a compute-bound code. Then moving into more well-known applications, we've used OpenFOAM, which is a widely used open source CFD package, widely used in different engineering contexts. And here we've used a certain benchmark known as driver. Again, this is a runtime, so lower is better, and we can see how things are doing here. OpenFOAM, again, largely classed as being memory bandwidth bound, although compute does matter for some phases of the computation. In this one, you can see A64FX kind of doing okay. We haven't got result from CCE for that code. The version of CCE, the Cray compiler, which generates the vector instructions for A64FX, that's an older version of the compiler that can't compile OpenFOAM. And the newer version of the Cray compiler, which can compile OpenFOAM, doesn't yet generate the vector instructions for A64FX. So that's why we don't have a result there. Code on the Ultra ran really fast, again, similar to 2 sockets of AMD Rome, which is very impressive. A64FX, we'd hope, would be a little bit faster than that because of the memory bandwidth. and it's not quite there yet. It's nearly as fast, but it's not faster yet. So again, still a little bit of room for improvement. Ultra, about twice, 2 Ultras about twice as fast as 1 Graviton. Thunder X2 somewhere behind. OpenFOAM is a code that also takes advantage of very large on-chip caches, and both the AMD Rome and the Ampere Ultra CPUs do have big, large last level caches, so they do benefit a lot from that. A62FX doesn't have a big last level cache, so it does pay a little bit of a penalty for that. So that's OpenFOAM. Still very impressive result for just 1 socket of A62FX being almost as fast as 2 sockets of Ultra, even though that's an early result. And then last one, GROMACS, which is a widely used molecular dynamics code, very heavily used in Europe, so that's used all over the world. Again, it can be a largely compute-bound code, becomes bound by the network at larger scales, but here we're just running inside 1 core. Here the performance is measured in pairs of bonds calculated per microsecond. So this is a performance chart, therefore higher is better. You want higher lines. Very high performance from the dual socket Ultra, pretty high performance from 1 socket of Graviton 2, and pretty good results from Thunder X2. A62FX so far, it was only with GCC we were getting good performance, and then it turns out that GROMACS has a very early version that uses the new ARM vector instruction set SVE, and that was only supported by GNU. Doesn't work yet with any of the other compilers, which means the other compilers weren't using that vectorization. They could only use ARM Neon, which is previous generation and only 128-bit, not 512-bit. So that means that GROMACS on the other 3 compilers really has both hands tied behind its back, and the performance in general with GNU on A62FX isn't great. So there's a lot more room to improve here. Eventually, we expect, while A62FX has got nearly 10,000 pairs per microsecond, back of the envelope calculation says it should really be much more closer to 40,000. So there should be a factor of 3, maybe more performance to come for GROMACS yet on A64FX, with some more optimization, some more refinement of the vector versions of the code, and a bit more polishing and a bit more support for the other compilers. But it's starting off promisingly. Our experience in running these codes on Isambard is that pretty much most things just work out of the box. We ran a hackathon a couple of weeks ago with 50 people porting and optimizing to A62FX, and most things just worked. Found a few small issues, but most things just worked. The compilers and libraries were already very stable. There's room to improve performance of the generated code, but there's a lot of support there already for these things. And support for optimized libraries and higher-level frameworks are continuously being improved as well. And even during our 2-day hackathon for Isambard, we saw a lot of improvements in things like BLAS libraries and so on, which was very encouraging. Now, of course, it's the trajectory of where ARM is going in HPC that's quite exciting. So we're showing you performance today, but things like this is the Apple A14 ARM core, which is inside the M1. It's what I'm using right now. It's inside the latest iPhones and iPads. And it's an 8-way superscalar, heavyweight, out of order processor. You have the reorder buffer is over 600 instructions large. Over 600 instructions can be in flight inside 1 core of this ARM chip. Super impressive. Big caches. This is class-leading single-thread performance. And of course, it's only going to keep getting better. So this is why ARM is such an interesting and exciting trend. See if we can exploit in high-performance computing. And of course, we've just had NVIDIA's announcement of their Grace ARM-based CPUs. Not many details released yet, but there are going to be lots of ARM Neoverse cores, lots of bandwidth for direct cache coherent links between Grace CPUs and GPUs, lots of memory bandwidth, 500 gigabytes a second per socket, not to HBM and not to DDR, but to low power, to LPDDR5. Which is quite a clever move because you get lots of memory bandwidth, but it's energy efficient. And performance, over 300 on Spec Rate 2017, which is similar to a dual socket Skylake or Cascade Lake system, but that's for 1 socket of Grace. That's a next platform report there, and then shipping year after next, 2023. So again, that's a very exciting option for future ARM-based HPC systems. So to summarize all of that, we've really been proving that ARM processors are competitive in high-performance computing since Isambard first went live in 2018. In a similar time frame, we had the Astra system turn online. That was the first ARM-based supercomputer that got into the top 500 at Sandia. And then over time, of course, there's been lots of other ARM systems around the world, at CEA and Barcelona. And then, of course, we can, with Fugaku being the number one, top of the top 500, being based on ARM for the first time. Two, and other systems we know are coming all around the world based on these sorts of technologies. In the meantime, the A62FX looks really promising. One socket of A62FX is beating dual sockets of lots of other processors in lots of our tests. It's been really easy to use, just runs your MPI code, your OpenMP code. Performance in some codes is on a ballpark with GPUs because of those high floating point rates, but really easy to use. We're not having to rewrite code in different languages. We can just use the MPI code and it runs really well. So ARM processors have really exciting roadmaps in both high performance computing, but also cloud. And we talked about Amazon, but there are other sorts of exciting things going on in cloud as well, all using ARM. And really nicely, we've been able to make many of these technologies all available in one place in Isambard 2, so that you can come and do some nicely scientifically rigorous benchmarking, all in one system with one software stack, using all the different compilers, comparing the latest, greatest CPUs from all the named vendors and GPUs actually with the latest ARM technologies. That's all in Isambard 2. And actually, you can, if you're interested, you can apply for an account on Isambard 2 and you can try this out for yourself. So for more information, I've got the link there for my research group, the University of Bristol High Performance Computing Group. You can go to the Isambard website and apply for an account. You can drop me an email or follow me on Twitter. And many of the results we just shared, they're going to appear in a paper at ISC in June this year. So watch out for that paper appearing. And that's everything I've had. Hopefully that's been interesting, and do get in touch if you'd be interested in trying out Isambard for yourself. Thank you very much.